Thank you very much, Neil. It's actually very humbling to hear this. But thank you for the organizers of the Joint Colloquium series for this opportunity to speak, and thank you for coming. I wanted to talk to you about modeling formation of galaxies in the hierarchical universe. Modeling is a present tense because this is still a continuous process. We have not done yet. And this topic is very vast, and I'll can only hope to touch on a sort of broad brush picture, to give you a broad brush picture of why I think there are exciting times in modeling galaxy formation, and give you an idea about what was behind the breakthroughs that occurred in the last few years in our understanding how galaxies form. In particular, I'll focus on formation of late type galaxies, galaxies in which stellar distribution is dominated by kinematically cold disk of the kind that you see here. And so the idea is that we want to understand how galaxies like this, which is actually supposed to look very close to the Milky Way, the way Milky Way looks like. We don't know exactly how it looks like, but we have some idea about its structure. So this is one of the observational analogs of the Milky Way, photoshopped into Deknaria halo that formed hierarchically in the best, in our paradigm of hierarchical structure formation. And we want to understand how galaxies like this form in a halo of the kind. The halo is real. This comes out from simulation, but the galaxy is photoshopped. Also, I hope that for people who don't know much about galaxy formation, by the end of this talk, you'll be able to understand what is wrong with this Photoshop picture. There's several things wrong, but there's one very silent one. The second part of the title, Order Out of Chaos, requires some explanation. This sounds nice, but also it actually encapsulates some, I think, key features that I think are key features of galaxy formation, where very chaotic processes, very violent and chaotic processes result in ways that are still quite mysterious, in a very ordered properties of galaxies. And I'll try to point out some of the evidence for this very ordered behavior of galaxies. The actual title was motivated, and I see Jim was trying to remember something. The actual title was motivated by Jim's paper, and and I should say that first of all, I chose this title not only here, so this is not for Princeton, and I had no idea that Jim will be sitting right there. At least you can compare the two images. And at one point, I stumbled upon this paper, and I thought had a lot of joy reading it, because I don't think people write papers in this language anymore. If you read about it, it's very lively. And Jim here talks about the situation in the early 70s, where it was the CMB was already detected, so we knew that hot Big Bang is the universe was started in hot Big Bang, but there was nothing known about fluctuations, not very much known about composition of the universe. And so there was this strong debates about the initial state of the universe, and some people argued that some people, Jim was actually calling them revolutionaries were arguing that universe was chaotic, very homogeneous, and without form. And then conservatives were arguing that it was isotropic and almost smooth. And I think, if I remember correctly, Jim has called himself a reactionary or conservative. And and that was because actually the simulations of this kind that he did in the early 70s did start with almost homogeneous distribution with fluctuations just due to Poisson fluctuations. And the gravitational stability resulted in structure that looked very much like observed galaxy cluster. This passage that opens the paper ends with this kind of reconciling statement that regardless of your political affiliation, whether you're reactionary or whether you're revolutionary, the whole debate has to be framed within some framework. And that framework was the Friedman-Robertson-Walker cosmology, and with perturbation that would allow structure formation. Since then, there's a lot of data acquired that was settled most of the debate that is alluded to here in terms of initial state of the universe. But we also know much more about composition of the universe. We know that in these two assumptions that needs to frame the debate and define the framework, there's another one, dark matter. Yes, we need dark matter also to have the framework for understanding how structure forms inside from the almost homogeneous isotropic initial conditions. Okay, so this is kind of a summary plot from a paper that was actually also done here by ACT collaboration a few years ago. This shows mass variance. So this is fluctuations. I need to this new pointer. This is mass variance in spheres that enclose a given mass, and so it gives you an idea about the amplitude of fluctuations on different mass scales. So the CMB that gives us proof that universe is almost homogeneous, but with small fluctuations at large scales, is here. It encloses significant fraction of the horizon of the universe, very large masses, and we have very precise data now there to constrain fluctuations. And then going down to small scales, we have clusters, and we have galaxies, and we have Lyman alpha forests that pretty much constrain the shape of this fluctuation spectrum, which agrees with the shape predicted from almost scale-free initial power spectrum once you take into account all the plasma processes that are going on in the early universe before recombination. The galaxy formation is controlled by the fluctuations on this part of the spectrum, where this function almost flattens, turns into a power law and tries to become very, very flat. If you consider galaxy formation over a narrow range of masses, we can approximate this function by a power law. And power law has no scale, so the first order, the fluctuations on the scales from which galaxies and groups of galaxies and clusters of galaxies form are scale-free. Gravity itself, when it controls collapse of the peaks, is also scale-free. So what ends up, what results from the collapse of such fluctuations is a complicated process where you have multiple peaks collapsing at different times and merging. So it's not, collapse cannot be described by a single peak collapsing. You have multiple peaks because there are fluctuations in different scales. And because the fluctuation amplitude increases towards small scales, it means that the first, on average, statistically, the first fluctuations that collapse are small ones, and they will merge them to grow bigger and bigger fluctuation. That's what makes the formation hierarchical, right? This process, because of this multiple collapse and multiple peaks, is very violent because mergers correspond to strong fluctuations of potential. And the best way to appreciate the violent nature of this is just to see it in motion, to see it in action. So here you see collapse of a single peak, where you can see multiple peaks collapsing because there is fluctuations present on all scales. And here you see only dark matter. But evolution is very rapid, although here the 14 billion years, 13.5 billion years is compressed into less than a minute of the movie. There's also a little bit rotation to show you three-dimensional structure. But if we look at it again, and you pay attention to what happens in the very beginning, you can see this very violent and rapid and very frequent mergers that are happening all the way pretty much to redshift 1 on average. And during this merger, there's very strong potential fluctuations and very violent dynamical processes. That's right, yeah. Although at a very more quiescent way. So the fluctuations of potential typically quiet down. I didn't tell you on purpose what mass I'm showing you, what scale of the peak I'm showing you, because to first order, due to the scale-free, almost scale-free nature of the power spectrum on the scales of that we consider when we consider galaxy formation, it doesn't matter if we just look at dark matter. This is illustrated in this image where you see two halos of mass different by 2 orders of magnitude, by a factor of 100. One halo corresponds to, in scale and in mass, corresponds to a galaxy cluster, something like a Virgo cluster. Another halo, the other halo is corresponds to a Milky Way-sized galaxy. But just looking at dark matter distribution in this very rescaled way, and rescaling here is done by what is typically referred to as the virial radius, or the edge of the halo. There are different definitions for the virial radius, for which we can use to rescale it. For the purpose of this talk, the difference between them is not particularly relevant. The one that I use here and will be using throughout the rest of the talk is the radius that encloses a density contrast of 200 relative to the critical density of the universe at a particular redshift. So when we talk about radius R200, what I mean is the radius that encloses a mass that is 200 times the critical density of the universe at the redshift at which I consider a particular object. So here, both objects are shown in a region that corresponds to their 4 times the radius of R200. So they are scaled. So the difference in scale and mass is taken out. And otherwise, just looking at dark matter distribution, you wouldn't be able to easily tell which one is a cluster and which one is a galaxy. I've tested this by quizzing the experts to tell me which one is which. And the answers have 50-50 distribution. So the answers are random. Okay, so here's an illustration. That's actually, this is the galaxy on the right. This is a cluster. And the reason is simple. It's not because we don't know our stuff. The difference between them is very subtle. There are small differences. So the deviations from the pure self-similarity are there, but it's very difficult to just tell from one object because qualitatively they are quite similar. Now, this is, most of you who know anything about astrophysics know that this is very different from the observable universe, because if we look at galaxy and cluster scale, so here galaxies on the left, clusters on the scale, on the right, here there would be no question of where is a cluster of galaxies and where is a galaxy. When we typically look at a galaxy, it's an object that surrounded by a handful of dwarf galaxies, very faint ones. We don't see lots of substructure around it. This is something that people discuss at length of how to understand this. But I think this is just a consequence of the overall breaking of self-similarity during the process of galaxy formation, right? So this is a visual visual.
Dimensionless numbers determine galaxy formation. Dimensional numbers.
That's right. Yes, due to the process that would break self-similarity. And this is a very striking visual manifestation of the breaking of self-similarity. To be quantitative, we can look at things like stellar mass-halo mass relation. So here you see a relation between stellar mass of a galaxy that is hosted by a halo, and this is observations. So in observations now we can probe halo masses. So the total mass surrounding the galaxy within this radius R200 that I introduced by a variety of ways. Some of them are weak lensing, and some of the measurements here were done actually here in Princeton by Rachel Baum and all, and by other people more recently, and they more or less agree to the accuracy to which this point has to be made. There is measurements through satellite kinematics. There are measurements on the cluster scale through X-rays, as United-Deutsch effect. And we see that galaxies fall into this pretty tight sequence, but this sequence has complicated shape. Just to give you a baseline, if galaxies would be able to accrete all their fair share of baryons in the universe, so everything that was present in the region, Lagrangian region, which collapsed into this R200 radius, and would be able to convert it into stars, the relation would just look linear, indicated by this dotted line, right? So we can see that the actual relation is both nonlinear, so it has slope of steep slope here, shallower slope, shallower than linear here, but it's also displaced quite a bit. So even at the point where the relations are closest, there is a factor of about 3 difference. Yes.
The shallow slope towards the high mass band is somewhat misleading. I know that's usually what it shows, because it really shows the baryons of the stars just in the central galaxy of the halo.
That's right.
It doesn't show all the baryons.
That's right.
Of the halo.
That's right.
And if one includes all the stars in the halo, it will become steeper.
It would become steeper, but still not linear. So the slope becomes. Right. The slope in that case, there is quite a few papers, including this one, from which this plot is taken. The slope, when we include all the galaxies, turns into something like 0.6. So still quite a bit different from linear, but steeper. You're right. But this, I think, is part of the physics that we need to understand. So part of the physics that makes relation nonlinear could be dynamical. The fact that you actually distribute stellar mass not in the central galaxy, but keep it in satellites. But this is part of what we need to understand about this whole relation, right? The scatter, I wouldn't say it's well constrained, but there are constraints on scatter. And the scatter about this plot is about 0.2 dex. So you can see the order of magnitude is here, so 0.2 dex is roughly here. So it's comparable to the scatter between the points, I would say. So there is a fairly tight relation. So the goal of galaxy formation, of course, one of the goals is to understand the processes that lead to this nonlinearity. What we think is happening is feedback. So stellar feedback that prevents collapse of baryons or ejection of baryons, prevents turning the fair share of the baryons in the halos into stars. On large scales, we think that AGN feedback has to do with the physics that shapes this relation. On small scales, where the black hole masses are relatively small, we think it's mostly stellar feedback. And this will be the subject, this particular mass scale. So starting about this characteristic mass and lower masses is something I will focus on in this talk.
A lot depends on those 3, but on the 2 at around 10 to the 11th solar masses, where weak lensing must be very difficult.
Right, except that yes, it is, but it's detected by stacking. So stacking a lot of galaxies, so it's a statistical signal. And what you can see here is there are actually two independent measurements. So there's one measurement by Hudson et al., and there is a second measurement also led here by Reina Reyes et al. So this, yes, actually, so LMC is expected to be in a halo of 10 to 11 solar masses. So we're actually, yeah, so we're probing down to LMC scale, which is pretty amazing. Definitely below this turnover. But regarding your comment, so the measurements of dwarf halo masses are difficult, but you can see that there is a line here. Actually, there is a set of lines, but the differences between them are not relevant here. So these lines are not a fit. It's not a functional fit. It's something that you can deduce from a simple assumption that to reconcile the observed stellar mass function of galaxies, distribution of galaxies, number density of galaxies, function of stellar mass, with a halo mass function that is predicted with great accuracy now, with the accuracy of a few percent for a given cosmological model, to reconcile them and the assumption that galaxies form in halos and each galaxy has a halo associated with them, you can actually just number density match those stellar mass function, expected halo mass function, and derive what the required stellar mass halo mass relation should be. And that is what you see as those lines here, with the difference being what you assume about the scatter between stellar mass and halo mass. So this is completely, it's not a fit, it's completely independent measurement based on this idea that, you know, to reconcile the stellar mass function that has power law plus exponential cutoff, well known since the early 70s, and the halo mass function that also has a power law shape and exponential cutoff, but at very different place and with very different strengths. You can see that, you know, if we want to assume that each galaxy forms in a halo, the relation between stellar mass, to reconcile these two shapes, the relation between stellar mass and halo mass, so this would be objects at the same number density, has to be different at different masses, right? So here, where you see a kink in the stellar mass distribution, it's the shortest. This is the characteristic mass that you saw in the previous plot. And at the dwarf galaxy scales and the cluster scales, it's longer. So there, the stellar mass is suppressed more relative to the halo mass. So this simple assumption that is known as abundance matching is reproducing the actual independent measurements through weak lensing X-rays pretty well. So if you want, this is an independent evidence, indirect evidence, supporting the assumption that galaxies form in halos. Well, you know, probably everybody in the room believes this, but this is a nice independent check.
So how do you handle in this description the fact that you put one galaxy in a big halo like 10 to the 15? There are hundreds of galaxies.
Yeah, so this just refers to the central. So
it's just the central,
yes.
but that doesn't tell you really anything
About the total. About, yes. Yeah, you can actually extend.
All those other galaxies are also in halos.
Yes.
That's right, but you have a 10 to the 15 solar mass system, right? It's one halo, and it has hundreds of galaxies, not one.
Mm-hmm.
And those
I
hundreds of
understand that they will
galaxies,
subhalos and they are
those
coming
hundreds of
together.
galaxies are in hundreds of subhalos.
So this is just one version where only you can only do this for central galaxies, but you can repeat this exercise taking into account subhalos and actually predict what the distribution of stellar mass of galaxies and clusters would be, and that works as well. That's actually been shown in a number of papers. One of the first was Jerry and with Whale. There's another. You can see the break of some similarity in other properties of galaxies. So I like this picture very much, because it encapsulates a lot of things about the population of galaxies. What you see here is a post-HSM collection, random subsample of slow digital sky survey galaxies, where on the y-axis you see color. So the color runs from red to blue, and the size of the galaxy from small to large. Each post-HSM here shows you roughly the same physical region around each galaxy. So that's why when you get to massive galaxies, they kind of crowd the entire field because they're physically larger. You can actually see by eye this breaking of cell similarity in this plot, because you can see that starting roughly at L star, so this is this luminosity of galaxies where the stellar mass function has a kink, has exponential cutoff. You can see that for larger masses, clearly as you go as you go to larger sizes, the galaxies become bigger, so there is a dependence of, and also morphology changes. But for a wide range of luminosity, by the way, this just steps in a given step of local luminosity of galaxies. So there is also size and luminosity running here. You can see that at low luminosities, there is barely any change in size, right? So you go in a step in luminosity, but the galaxies roughly remain the same, right? So there is a very weak dependence of size and luminosity and for faint galaxies. And there is a fairly strong dependence for massive galaxies. So we know that relation between size and luminosity, or size and stellar mass of galaxies, is not linear also. You can see it quantitatively in this figure where I show you the half-mass radius of stellar distribution as a function of stellar mass of galaxies for pretty much the entire galaxy spectrum, from this faintest dwarf spheroidal galaxy that you see here. Their stellar masses are just 1,000 to 10 to the 4, so they're smaller than some globular clusters, with sizes of just tens of parsecs, all the way to the brightest cluster galaxies, which sit in halos of 10 to the 15, have stellar masses of more than 10 to the 12, and have sizes of up to 100 kiloparsecs in terms of their half-mass radius. You can see there's highly nonlinear relation. So it has this curve. This is what you saw in the previous image, almost no dependence, very weak dependence for small galaxies, but then dependence that picks up for massive galaxies. There are differences, some differences between late and early type galaxies, red and blue. The Milky Way, by the way, is a star here. So this is our galaxy. It sits roughly on the median relation for late type galaxies. But the overall relation looks complicated. Nevertheless, there is a very significant order here. So first of all, there is a relation at all, which is interesting. And as I'll show you in a couple of slides, this relation is completely set by the properties of halo, which hosts the galaxies. How can we see this? Well, all we have to do is to convert the stellar mass to something that relates to halos. We know now, we have good ideas I showed you about the relation between...
According to these figures, there's two branches at the low end. The dense ones and the M32 would be way above that.
That's
You
right.
only showed one branch.
Well, so if you look carefully here, there are two branches.
The low mass end. Low mass
Here on dwarf spheroidal, I don't see. So this is a collection of very high resolution images of dwarf spheroidal, dwarf elliptical, and dwarf irregular galaxies. And for this collection, I don't see any difference.
I agree with you what you said. But there's another branch that commonly shows of the compact ones.
Very compact ones. Yes, they may not be here.
M32 would be off this.
Okay, yeah. Or maybe it's just on the tail end of you can see that there is substantial scatter, and there is a tail end here. Right. So you can also notice that the stellar, so this inflection that, actually, let me go back. The inflection that you see in this distribution, if you look at what stellar mass it corresponds to, it's roughly 3 times 10 to the 10, so it's the same mass where we see the inflection in the stellar mass function. Again, the same characteristic mass that we saw in the stellar mass-halo mass relation, that also rears its head in the stellar mass size relation as well. Probably not surprising. But if we recast this relation in terms of correlation of galaxy size with halo size, which we can do using the stellar mass-halo mass relation, so this is something that we have a good idea, as I showed you now. From M200, we can compute R200 because they're just related by definitional equation. So for a given stellar mass, we can convert stellar mass to halo mass and then to R200 and construct this relation instead. So all we're doing is just changing the variable, right? Nothing much. But this change of variable gives a very quite different picture. So here, the distribution does not show a strong linearity and strong kink. In fact, it is consistent with linear relation, which is shown by this dashed line. So here is again the same three-dimensional size as a function of halo virial radius, the same galaxy that you saw in the previous plot from dwarf spheroidals to brightest cluster galaxies. But now you can see that for each galaxy, the size is roughly proportional to 1 to 2% of the virial radius. So R1/2 is just for each galaxy, I know stellar mass. And I apply average stellar mass-halo mass relation. So it's an average. So the half-light radius is just something you measure from the surface brightness profiles. Yes, that's a vertical axis. That's observational measurement. The stellar masses you get from luminosity, and you get the, yes. That's observed. And the conversion, yes, the conversion to this radius is using stellar mass-halo mass relation. It also is constrained by observations, right? So it's not theoretical. Right. So we can see that this looks very different. So the size of the galaxy is actually just linearly proportional with a scatter, but linearly proportional to the halo radius, so this radius of the arc of
Andrey, where do these extended low surface brightness galaxies recently discovered by Dragonfly or Stroma, I mean, where do they fall in this relation?
They fall, I think. So I know what you're talking. Yes, I know what you're talking about. I think they're falling actually close to the upper edge of the distribution.
So they're not spilling over to higher.
I don't think so. And I should say that this dotted line. So the significance of this is that first of all, as a function of halo radius, we see no scale. So it means that the size actually knows very well about the size of the halo. Not surprising by itself, but the fact that this relation is linear means that the halo actually controls what happens to the galaxy size. And this linear relation is very close to what is expected in simplest models for how disks of how galaxies form, in which it is assumed that the specific angular momentum of baryons is comparable to specific angular momentum of Dirac halos, and when baryons collapse, the specific angular momentum limits their collapse and sets the disk size. The simple model predicts roughly this relation within a factor of 2, and this factor of 2 can be debated of whether it's consistent or not. And they predict that the scatter around this relation should be roughly given by these dotted lines. Right now, I don't think we have a good idea about the scatter in observations. This is a collection of different samples, but nevertheless, it's quite consistent. So there is a log normal scatter, which is quite substantial about this relation. But the key is that the relation of galaxies is consistent with what we expect in the simplest picture, where the specific angular momentum of baryons is reflecting specific angular momentum of dark matter. I would not before I made this plot. Now, after I made this plot, I started thinking: so how come ellipticals are falling on the same distribution? Yeah. So.
But do you really want to have L-star ellipticals rotation supported?
Well, so I think the interpretation of this is more subtle, but I think can be sort of so. For ellipticals, you can't think about the size as being set up by a rotationally supported disk. But if you think about individual orbits, the angular momentum of individual orbits still can reflect the angular momentum of accreted material. It's just something had to randomize the orientations of the orbits.
You
Right?
end up lots of rings at a lot of angles.
But you didn't do that for spirals.
That's right. So spirals ended up in coherent disks, whereas ellipticals, the orbits were randomized, right? But the average angular momentum and energy of the orbit still apparently reflect the energy and specific angular momentum with which baryons were accreted. And in that respect, there is not much difference between ellipticals and disks. Where you will see the difference, and I'll show this plot towards the end, is if you compare specific angular momentum of disk and elliptical galaxies. Specific angular momenta are very different. That's right. So I think the way to understand it is to think about angular momentum of individual orbits, which still remembers the angular momentum with which the baryons came in.
It's really striking that you have the bistability here.
Yeah. So I showed you just a few examples of what we learned about galaxies in the last couple of decades. And the striking thing, I think, is to understand how regularities like this, how size of galaxy can still remember with such accuracy, or can be so simply related to halo radius, while we know that there are strong processes that break self-similarity that you could see in chaotic processes that break self-similarity, both due to the dynamical nature of the collapse involving mergers, but also due to feedback that is also a highly chaotic process. How this can be reconciled with the simplicity that we see which is revealed in relations like this of the size between the size of the galaxy and the halo virial radius. Right. So this is a task for galaxy formation to understand. I think we understood the basic features of how galaxies form in these models for 20 plus years. In fact, this was an image from one of the early papers, and there was a few pioneering papers that appeared in the early 90s. There's a paper from Neil Katz, which I think was part of his PhD thesis here, where you can see collapse of dark matter. This is just two different snapshots in time, early and late. This is redshift 0, I believe. Dark matter, gas particles, star particles. And you can see that pretty much these violent merging processes that are you could see in evolution of dark matter. You could see also in gas. Of course, they share potential. They share the evolution. But dissipational process of gas lead to dissipation, condensation of baryons towards the centers of the dark matter potential wells. And so that's why the distribution of baryons looks more knotty, more concentrated. And then the stars form in the densest regions of the gas, and the stellar distribution is the most concentrated. You can see that by redshift 0, there's still some signatures of this pulsed violence, but overall halos are more relaxed, and galaxies are more relaxed. But they tend to be very compact, and although you can see some of the disk, the actual size of this disk is quite a bit compact compared to where we put galaxies of the stellar mass. So the issue, although the overall features that you can see galaxies forming through the sequence of merging and qualitatively form a disk structure with a spheroid, something that was very striking when I first saw this paper when it came out. And in fact, when I saw it first, I thought, well, I'm late for this modeling. I'm not going to be able to contribute anymore. At that time, I didn't realize that actually the problem is very much more complicated and will take quite a bit, some decades more of work. And so this was not too late to contribute. But this was so it was both impressive but also disappointing, because after this initial success, it was realized that quantitatively the galaxies that were coming out in the simulations were not quite correct. And it took 2 decades or so, and maybe more, because I don't think we are quite there, to really improve upon this. And one of the problems that arises in the simulations that you simulate a galaxy in a halo of 10 to the 12 solar masses, which we believe should host on average, a late-type galaxy like the Milky Way. And what you get is a variety of systems. So different halo masses have different merger history, and so you can expect a variety of different galaxies to form. And you form a variety of galaxies, but as you can see here, and this is just one example, I'm not trying to pick up on any particular study, this was very generic result that was coming out in all kinds of studies. What you can see is that you form different galaxies, but in each case, there is a very strong, massive spheroidal component. So each galaxy has a very massive, what astronomers call bulge. And bulges, of course, exist around many galaxies. Many galaxies have lenticular shape and elliptical, but we also have late-type galaxies denominated by a kinematically cold disk, in some cases without any signature of the bulge. And so this formation of such systems of very thin kinematically disks, almost bulgeless, which remained the challenge for 2 decades, because pretty much all the galaxies that were formed were like this. Now, the reason for this is because the simulations try to include all the relevant physics that we thought was controlling galaxy formation, but some pieces of this physics turned out to be quite challenging. In particular, the stellar feedback, and AGN feedback, I think, is even more challenging, but the feedback overall turned out to be extremely challenging. So this is an example, for example, where things were a few years ago, around 2012, actually, some of the simulations 2014, but this was very representative of the situation a few years ago, where you see the stellar mass halo mass relation. So this is the same plot as before, but now showing you not data but simulated galaxies by 3 different groups, just to show you that results from different groups of different codes were quite consistent with each other. There was no difference. It wasn't a question of using particular code or particular scheme. The codes were different. The schemes that people use for star formation and modeling stellar feedback was different, but results were quite the same. At small masses, you could see that simulations are producing galaxies very close to the dotted line, which corresponds, to remind you, to the case where galaxies would accrete the entire fair share of baryons from the region that collapsed into a halo and converted all those baryons into stars. So this is relation where galaxies would essentially be self-similar. So the stellar mass would just be proportional to halo mass. We know that the real galaxies don't do that at those masses, that this relation is very steep there, and something suppresses the stellar mass. Then, as you go to higher masses, you can see that there is a deviation from the dotted line, but the deviation is very mild. So at the scale where the real galaxy exhibits a strong characteristic feature, the bend in the stellar mass halo mass relation, the simulations did have a bend, but very subtle one. This bend, I think, is related to the physics, the thermodynamics of forming hot, massive halos for potential wells of about 10 to 12 that can support viral temperature of the gas of about 1,000,000 degrees. That was advocated by Jerry and Martin Rees in the late 70s. But by itself, as the simulations show, this thermodynamics was not quite sufficient to generate a very strong deviation. So this deviation, this thermodynamics has to act in conjunction together in coordination with stellar and AGN feedback, in order to create this very strong scale. Right. Now, simulations that you see here did include feedback. So you can ask, so how come they didn't reproduce the scale? Well, the reason was that feedback that they included was not sufficiently efficient, was not doing the job. Right. This fact that it was not doing the job, that it was producing the stellar mass-halo mass relation that was very different from real galaxies, is actually something that allows us to understand the problems of galaxy formation simulation, why they were having trouble forming late-type galaxies. Right? So one effect is that massive disks are unstable. So when we form a galaxy, if feedback cannot remove the gas from the galaxy, if it allows gaseous disks to become massive, we know that massive disks are unstable. This is something that was understood from early 70s, from the work of Jim and Jerry, but also shown in numerical simulation by Astrophysics and subsequent authors. We know that when disks become self-gravitating or close to self-gravitating, they become unstable. When that happens, the strong gravitational stabilities that are generated lead to loss of angular, redistribution of angular momentum, and formation of a central dense concentration. For a long while, simulations, when we looked at them, formed very quickly, very rapidly at high redshifts, very dense central concentration that produced a strong spike in rotation curve, and which was not realistic compared to real galaxies. And I think this is related to the fact that feedback was not producing galaxies that were way too massive here. So the disk was massive. You can see that the actual results from the simulations of this process, which indicate the region of stability. This is a specific, essentially, parameterization of specific angular momentum of the disk as a function of the fraction of disk mass relative to the halo mass. So the simulations show that this has to be, in order for a disk to be stable, the galaxies have to live on this part of the diagram, in the upper diagonal, upper corner of the diagram. But we also know that the real galaxies live in this region, because on this end, they are limited by the universal baryon fraction, for how many baryons are available to them. And on this end, they just are limited by the ability of tidal torques during collapse of the halo to generate sufficient angular momentum. So real halos, real galaxies live in this rectangle. You can see that they could be either unstable or stable, depending on where they end up in this diagram, right? So for this to be stable, it has to be here, which means that the mass of the galaxy has to be kept within a certain fraction of the halo mass. And the only thing that can do that is stellar feedback, because without it, as you could see in the previous diagram, the fraction would essentially be close to the universal fraction, which is about 0.16. So galaxies by themselves, without feedback removing the gas from the halos, would like to be somewhere in this part of the diagram, which would be unstable. Right? So this is one reason, and the stability is here. That's one reason why the simulations were producing very centrally concentrated, spheroid-dominated galaxies. The second reason is, again, if we look back on this diagram, is that a galaxy like a Milky Way would form by mergers with galaxies of smaller mass, which actually would contain significant stellar mass in them. So when you have stellar mass mergers, the only thing they can create is spheroidal component, because in mergers, the orbits of stars get randomized and create a spheroidal distribution. There are two processes that work together when the stellar masses of galaxies are too high. The disks are unstable, and the mergers lead to creation of spheroids. Okay. So the feedback can solve, turns out, they can solve both of them. But the issue was that the implementation of the feedback is challenging. And it's easy to understand why it's challenging, because feedback connects the scales that are just few parsecs to scales that are hundreds of kiloparsecs. The feedback operates at the scales of individual star-forming regions, so example of which you can see here, this NGC 604, with cold gas and dust shown in this purple, and the blue shown the shock-heated hot X-ray emitting gas. And here's a young star cluster that is creating this, blowing up essentially its natal environment, dispersing the gas. And you can see example of M82, very large-scale winds, where combined action of regions like this gets combined into large-scale outflow. So in simulations and models of galaxy formation, we have to include at the smallest resolve scale, which is right now in the state of the art simulation just tens of parsecs, while we're modeling a galaxy collapse and evolution on a megaparsec scales.
So the alignment in M82 is not properly AGN?
I think is that you can get such biconical outflow even if it's stellar feedback and it's concentrated toward the center of the galaxy, because the gas goes into the path of least resistance, essentially, which is perpendicular to the disk. But AGN can create biconical outflow as well. Right. So this is what makes it difficult, but it also means that we really had to pay attention to how the star formation and feedback are implemented in simulation. And this is where actual progress, the main reason why the progress occurred in the last 5 years. Essentially, people, facing the repeated failures of simulation to produce late-type galaxies, people have re-examined how star formation and feedback were implemented. And there are several things that were noticed. One is that it matters how you convert gas into stars. For example, which portions of the gas, whether you just take a dense gas inside your galaxy or you take lower density thresholds for allowing gas at lower densities to form stars. That mattered in terms of how efficient feedback was and the kind of galaxy that you formed. It also mattered how you redistribute the energy. There are different models proposed for how young stars could inject momentum and energy into surrounding interstellar medium. Some processes like radiation pressure, some processes like stellar winds, pressure generated by warm gas ionized by stars or H2 regions. Details here, the actual specific details of those different models do not matter. Because results that coming out from different implementations are quite similar, which means the details actually are lost. But one feature that is similar between those different implementations is that the energy and momentum injection by young stars are resolved in time. So you don't just dump energy at one time, but rather you actually try to model the process of how energy and momentum is injected by young stellar population in time. The reason it matters is that initial injection of momentum by say H2 regions or winds or stellar pressure can disperse the very dense gas from which stars form. And then as supernovas start to inject their momentum and energy, they do so in a low density environment. That's one explanation for why implementation of feedback became very efficient. Overall, I want to stress again that the key thing about the progress, and I don't think we are done with understanding this process, it was to try to look closely in how we should model this loop between star formation and feedback. I like to depict it as an Ouroboros. This is a snake or dragon's biting its tails, because really we have to think about both. When we think about the feedback comes from young stars. Young stars come from star formation. So to understand the impact of stars on galaxies through feedback, we need to understand both star formation and feedback, because they're really connected. How much energy and momentum you inject depends on your model of feedback, but ultimately it's normalized by the number of young stars that you form in a given location, and also the distribution of stars in the galaxy. There is a very large number of works, of which this is just a sampling, in which this was done, and very encouraging results were obtained. I'll show you just example of our contribution to this process, in which we try to understand effect of parameters related to star formation and feedback on the formation of Milky Way-sized galaxy. This is work I've done with Oscar Aggerts, who used to be at University of Chicago, now University of Surrey, in which we simulated a Milky Way progenitor of a Milky Way-sized galaxy, so a galaxy forming in a 10 to the 12 solar mass halo, with adaptive mesh refinement simulations. And there are many details of numerical details of simulation, but the key things that I think are relevant for the discussion are the two. So first of all, the modeling of star formation was improved somewhat relative to, say, typical simulation a decade ago, by using modulating the star formation rate with molecular fraction. So we allowed star formation only in the regions where rich in molecular gas. This typically concentrates star formation into very dense gas, the regions where would be sufficient for formation of molecular hydrogen and self-shielding. The second thing that we improved the model for radiation for the stellar feedback by including processes like radiation pressure, injection of momentum due to stellar winds, and so on. But again, details here maybe not so relevant. The relevant thing is that these processes were done in a time-resolved manner. So injection was done in time. There's also, for some simulation, we included the model for subgrid model for cosmic rays. And we run simulations of the same halo, so pretty much the same object rerun, just varying parameters, a few key parameters. One of the parameters we varied was this one. This is efficiency per free fall time. So this is star formation efficiency. So if the fraction of gas that would be converted into a given cell per free fall time and the time scale on which it would collapse. Typically, what we know about star formation is quite inefficient. So this parameter is quite small, and we varied it from in the range between 1% to 10%. For individual molecular clouds, this is a range that is consistent with observations.
So blue gas is defined on your resolution?
Yes, this is roughly at resolution, which is one of the challenges. Yeah. So just to give you an idea, so here's a subsample. We actually run about 8 different models, but here's a subsample of star formation rate versus redshift. And you can see a subset of the simulation. One simulation, which I would call weak feedback, is this one, where we compare star formation rate with what we expect for the halo of this mass. So this is expectation derived by sort of semi-empirical modeling by Beruzzi et al. What we expect star formation history of a typical Milky Way galaxy to be as a function of time. There is, of course,
This is Zoom simulation.
this is Zoom simulation.
So it includes cosmological.
Yes, everything is fully cosmological. Yes, and so essentially we want the reality is somewhere where this gray, where you see this gray band. Everything about simulations are more or less the same. They're just parameters are different that we include for feedback. In this case, we included we used the efficiency per free fall time of 1%, and you can see that the star formation rate becomes large, and essentially it's quite a bit above this relation that we expect. If we change, the only thing we change is just efficiency per free fall time, so nothing else has changed. This model for feedback is the same, but the efficiency per free fall time is 10 times larger, still pretty much within the observational, consistent with observations. We get result that is much more consistent with this expected gray band. Now we can achieve almost the same result by using a small efficiency, but boosting energy and momentum input of each supernova. So in this case, it was boosted by a factor of 5 quite arbitrarily, but you can think about it as just having a different IMF or something like this. But we just wanted to explore the effect of something like this. Then the suppression is also quite high at high redshifts, but then at low redshifts, the evolution becomes quite violent, and star formation rate fluctuates quite a bit, undergoing very strong bursts. Now, yeah, so that's a bit counterintuitive, but this is a key, I think, to understanding the effects of feedback. It self-regulates. So you jack up your efficiency, but by blowing out the gas, lowering density of the gas, it actually ultimately, after some cycles, it lowers star formation efficiency globally. Yes. We're still running that simulation, actually. Yeah, so that's, but it's qualitatively similar to this red line. So I think the resulting galaxy will be quite similar. So if the difference between these simulations don't look dramatic, let me show you what it takes to go from this dashed line to this solid line. So this change of 10% of efficiency. What it in the same initial conditions, yes. Right. So what it entails in terms of evolution of the galaxy, what you'll see is evolution from redshift of about 10 to redshift 0 in the region of about half a megaparsec around this main progenitor of the galaxy. And you see here the temperature of the gas, and not anything else, just temperature. So you see the forming structure, the main progenitor of the galaxy is forming here. Everything lightens up. This is reionization. Then the shock heating, when the gas accreted gets shock heated. Slowly, the halo reaches mass of about 10 to 12 solar masses. It builds up million degree Kelvin halo that then slowly expands its radius as the halo grows. You can see this violence, the chaotic nature of galaxy formation in mergers of very cold, in the center. So this is very blue is cold. So here it's 10 to the 4 Kelvin. Very dark blue is about 1,000 or hundreds of Kelvin. So inside this galaxy. But pretty much you see that a lot of mergers, a lot of violence, but the halo itself very slowly grows, and you don't see very large scale outflows. The only outflows you see here were just dynamical in nature, driven by mergers and shock heating of the gas.
The white gas is expanding outwards at what temperature?
That's like 10 million degrees, yeah.
So red is hotter than white?
Actually, this is probably close to a million, and the 10 million in the center. Yes, that's right, yeah. And you can see that subsequent mergers, for example, send new shock waves that are propagating outwards, right? You can also see that after this last merger, you form a gaseous disk, but it is dominated by very big central concentration, which is very rapidly rotating. You can kind of see it, it's spinning like crazy. So the formation of this condensation was due to those instabilities I was talking about. because in this case, you don't see any strong outflows. The mass of the disk becomes quite large, and it doesn't satisfy stability criterion, so the disk is highly unstable. Right?
And what is the scale here?
The scale is, the overall is moving half a megaparsec. The scale of this disk is, this whole thing is about 5 kiloparsec, but if you actually look at half mass radius of that galaxy, it's about kiloparsec or less.
But the whole thing is
270 kbc.
Yes.
So
270 is actually half of it, so it's about half a megaparsec.
that blue streak is then the larger.
Yeah, but it contains very little mass. So what you see in this case is actually exactly the same object. So you can kind of recognize that the same large-scale structure from which it forms, starting at redshift 10. And the only thing that changed in the simulation is that we changed efficiency per freefall time. Changed nothing about the feedback, just a parameter controlling the efficiency of star formation to 10%. You won't see ionization in this case because before ionization happened, the whole region is filled with hot gas that now has very different origin. It's shocked gas created by supernova in the center, so forming galaxies that drive large-scale winds. It looks really like a bunch of explosions. In some cases, you can see that the entire volume that was reionized before was filled with shocked gas driven by stellar winds, by galactic winds. In some cases where you see these mergers, you can see events when the entire ISM of the galaxy gets dispersed. So the contrast between these two different runs is what it takes to lower the star formation rate at high redshifts from the high star formation rate to the region where we think real galaxies behave, where real galaxies live, right? So it's very highly violent, highly chaotic. And again, the puzzle, kind of the interesting thing to think about, how after all this chaos, the galaxies as ordered as we observe in the real universe come out. You can wonder, you know, how can this galaxy come out from this process, right? That is so violent. Nevertheless, yeah. That's right. That's right. Yeah. So I would not advocate this is some magic number or something like. In fact, I think it's probably resolution dependent, and also that's right. And one of the issues I think is that we treat this number as some universal constant when in reality it's not a constant, and it has to be explored how we actually can model this given its importance. And so you can wonder whether a realistic galaxy can form in a simulation. The answer is yes. So despite all this violence, if we look at the evolution of what kind of galaxies ends up in each of these runs. So the first run that you saw is this one, where the galaxy we form is very essentially concentrated. It's dominated by spheroid. There's a gaseous disk, but containing very little stellar mass. And the galaxy that looks very violent, and which is where the very strong large-scale outflow is this one, where essentially it's a late-up galaxy with correct disk-to-bulge ratio. Correct size on this size stellar mass diagram. This is the galaxy that you see here.
You're plotting stars.
Here's the stars, yes. So this actually HST mock-up images. So this is what HST would see in its filters, including.
Pretty visible stellar halo, but maybe there's a lot more light in the disk.
That's right. There is a very strong kinematic disk. There is a question still whether the disk is actually as kinematically quiet as the real ones, but it's close.
And what's the stellar mass function in that bulge at the center?
20%. Yeah. So it does have a bulge, but fairly small one compared to galaxies, typical galaxies of that size.
Is that typical?
It's fairly typical, yeah. For Milky Way, I think people are debating what the bulge mass is, but with a bar, yeah. But for other galaxies, 20% bulge fraction is not crazy. So the sizes, but something completely non-trivial is that the stellar surface density, so the simulation that was very violent with strong feedback is shown by this blue line. This is stellar surface density in the gas surface density compared to real galaxies from a single sample shown by dashed line. And you can see that it matches pretty well. So it means that not only the size is correct, but the actual surface density profiles are correct. So surface density profile is a result of very complicated evolution, redistribution of angular, acquisition and redistribution of angular momentum, and so on. And that's something that comes out of all that violence, which is quite encouraging. This is for the gas. The gas here, in terms of shape, is also quite similar, but is a little bit different in amplitude, which indicates that galaxy may be somewhat too gas rich at ratio 0, but not by much.
Which ones were best on this?
So
Which efficiency?
this was the simulation with 10% efficiency that I showed you the movie for. The second one was where we used 1% efficiency with boosted supernova feedback by a factor of 5. And in this case, the galaxy that forms has roughly correct stellar mass, but it has very large size and not quite correct exponential, but very extended distribution of stars and gas. Right. In terms of angular momentum, so angular momentum is something that was problematic in distribution of galaxies, which is related to the fact that galaxies would form in simulations were dominated by spheroidal component that would have very low specific angular momentum because angular momentum in individual orbits were canceling out. So this is something that was difficult to reproduce for simulation. So here you can see comparison of specific angular momentum as a function of stellar mass from a recent compilation by Fall et al. For galaxies of different morphological type here. And the simulation with strong outflows ends up here, somewhere close to early type disks. The simulation that you saw in the first plot where the feedback was weak has very low angular momentum, so it's a typical angular momentum problem that simulations have been suffering for 2 decades. And the simulation with boosted feedback is somewhere in between.
Right? Units are kilometers per second per kiloparsec.
Per kiloparsec, yeah, that's right. There should be another slash here.
8 kpc, you have 800.
Actually, no, it should be much more.
10 to the 2.
Sorry.
At 10 to the 2,
Mm-hmm.
which is roughly where you're running,
Yeah.
and 8 kpc, I have 800 kilometers per second.
Yeah. You're computing for Milky Way or something like this. It should be right somewhere here, right? So Milky Way is here, huh?
Wait. You don't want 800 kilometers per second rotation.
No, so this is already multiplied by kiloparsecs. So this is velocity multiplied by kiloparsecs, right? So it's an angular momentum.
kpc is in the numerator or
Yeah, no, numerator, because this is velocity multiplied. It's specific angular momentum, so it's, yeah, so it's V multiplied by R. Right?
It's r cross
Yeah.
v.
Yeah, so Milky Way would be 200 kilometers per second, say at 8 kiloparsec, it would be roughly 1,000, so it would be right here, right where this points are, right? And the galaxy in this simulation, you can see it quite close, so it's close to early type galaxies. So by all respects, just somewhat surprisingly, just trying 8 different combinations of parameters, one of them gives us a very realistic galaxy. Now, I think there's something, you're skeptical. I think there's something both profound and unsettling in this, because on the one hand, there is very strong sensitivity. Remember that all of these things, so all these different galaxies you see here, form in the same halo, in the same initial conditions, right? So you should be very skeptical from about any results from simulation from just a single implementation of feedback with single set of parameters. It tells you that if you change implementation, if you change your parameters, things will change pretty drastically, right? Still, out of 8 tries, there's one galaxy that came out to be quite correct. It means that the region of parameter space in which which may correspond to real galaxies, how well they correspond to real galaxies, is still to be determined. But this region is quite large, right? Otherwise, it wouldn't be so easy to find it. The second, despite the strong sensitivity to the parameters, that sensitivity has a very peculiar nature. It means that once we find a set of parameters that reproduce, say, a star formation history of the galaxy, this object here, the main feature about it is that it tracks the expected star formation history of the galaxy of that mass very faithfully, right? That by itself is non-trivial fact. But it means that once you get that right, a lot of other properties of galaxies fall out right for free, right? That's something highly non-trivial. It means that the sensitivity has very strong limitation, right? So once you hit a correct regime, the galaxies sort of go into a Tractor solution that corresponds to where real galaxies live. It means that it's not hopeless, despite the strong sensitivity, to learn something about how real galaxies form from this type of simulation. And by the way, I think part of the success that for the formation of disk is the fact that in this case, the disk was maintained by feedback, contrasting to this with feedback case, much closer to the stability region that is expected from basic stability considerations. And right, so this is a stellar fraction in the central galaxy, total baryons. So essentially, it's a mass of the central disk of the galaxy in units of universal fraction. And from stability consideration, we expect that this should remain stable if its mass is close to this gray region. So when feedback is weak, you can see that disk that forms is way too massive, so this can be expected to be highly unstable. What feedback does is that it keeps, for significant fraction of the evolution, it keeps the disk much closer to the stability limit. So I probably should, I will end in 1 minute, but just to end on a somewhat sour note is that, to illustrate that we're not quite done yet, when we try to compare, to make comparisons of these runs to something more complicated, in this case, circumgalactic medium, the gas around galaxies, we found that the simulations reproduced the stellar properties of galaxies very well, was actually quite failing quite dramatically on the distribution of gas. And I won't go into details of this, except that I say this is something that's already published. We found, published a couple of months ago, we found that somewhat annoyingly, the simulation had very strong feedback and produced a galaxy that was very extended and not quite right. Actually was producing CGM that was very close to observations, whereas simulation that was producing very correct galaxy was failing in the properties of circumgalactic medium quite the covering fraction, so this is the example of magnesium-2. So the covering fraction of the warm 10 to the 4 Kelvin gas within the virial radius, that observations indicate that this fraction is very, very large, whereas the simulation that produces a nice galaxy essentially has hot halo with some magnesium-2 absorption arising right close to the disk, but essentially empty outside the large radius. Not in this case, but in this case we did, and they help in this, and that's one of the hopes. They help, but they don't quite match the observation. So in the implementation we included, they didn't help to the fullest, but they help to move things in the right direction. That's right. Oh, that's interesting. So they help because the feedback associated with cosmic rays operates quite a bit qualitatively differently. So what happens is that supernovae inject cosmic rays, but the cosmic rays have ability to diffuse, or at least you can assume that have ability to diffuse. So as they diffuse out of the disk, they form a cocoon, a high-pressure cocoon, and a large-scale pressure gradient. Then any gas that gets ejected from the disk by supernova, even if it's not ejected very far in the fountain, finds itself on the pressure gradient that's pointing outwards. So essentially there is a pressure gradient that can counteract the gravity, and it becomes much easier for the gas to flow out. So this leads to gentler and more sort of coherent outflows of galaxies compared to the very violent outflow that you saw driven by supernova. They slow down, but essentially they produce a winds, but winds that are much steadier and can drive very warm gas.
Not the bombs.
Not the bombs, yeah.
So the observed CGM is more consistent with a strong feedback simulation?
That's well. I should say that there are two simulations here that have very strong feedback. Actually, the simulation that has weak feedback is this one, which we didn't run to redshift 0 because it was clear that it was very incorrect. The other simulations all have very strong feedback, but they produce very different gaseous halos. That by itself, I think, is highly interesting because it means that gas around galaxies has a lot of information about how feedback operates. The galaxies that were produced in the simulation were different, but gas was also very different, and different in sort of orthogonal direction.
So the difference between the two, what exactly is that? Here the producer just right feedback doesn't give you the right.
That's right.
CGM.
Right. The qualitative difference is that
Galaxy looks right, but the CGM looks wrong.
it looks wrong. But right. But what Nita is right. What Nita is asking is what is that? What feature makes it more correct? So the feature that makes this closer to observations is the fact that in this run at low redshifts, the feedback is still able to drive fairly large-scale outflows. So you can see these tongues of warm gas emanating. Right. So this is a results of recent outflows. This is column density. Yeah.
Yes, and that's not going to give you. Does the gas stay ionized at that surface density? No,
it is ionized. Yes, it's magnesium-2 column density. That's right.
So what about H1?
So H1 is also quite. I don't have a plot here, but we do compare in the paper. So I think it's a good stopping point. So it's like we actually already went into question session. the main